My name is Lieutenant Colonel Fausto, and I will present this paper, Reference Values for Damage Predictions of Reinforced Concrete Slabs Subject to Blast from Field Tests. We worked with this paper Mr. Joseph Mairink, Dr. Fausto, Dr. Girum Urgessa from George Mason University, and Dr. Fritz from ITA. The goal of this paper is presenting survey damage caused by the main terminal effects observed in recent studies on the behavior of the most commonly found construction materials. Especially, we are going to talk about blast effects against reinforced concrete structures. Especially, we're going to talk about slabs. Slabs made from reinforced concrete in this structure. We will follow this summary. We're going to talk about the introduction and talking about the explosion effects and so on. So after that, we're going to talk about the material and methods, what we did to work with this kind of survey, and the results and analysis, the comparisons that we did working with the results that we have in the literature. And after that, we're going to talk about a conclusion. The conclusions pointing what we could find in this survey that we worked with slabs that was tested in field tests, blast effect field tests. Talk about the introduction, what we can talk about the explosions. Explosions are generally large amounts of energy that is rapidly released after a physical or chemical or nuclear explosion. We're going to talk especially about chemical explosion because chemical explosion we have exothermic reaction and release of heat and gas that can cause damage and injuries for people that are close to the explosion point, and the structures around generally they have damages after the explosion. The temperature, the elevation of the temperature is one characteristic, high temperature around the explosion. The pressure elevation, we can see this picture here when you can see the shock wave that is generated after the explosion. And high pressure produces a shock wave. This shock wave we can see in this picture. And this shock wave brings damage for structure, people, and so on, many things that are surround the area of the explosion. There are many damages that we can see. So chemical explosives are used in aerial weapon, generally for helicopters and airplanes. Shockwave and fragmentation are the main effects that we can find in this kind of weapon. And high explosives became primary elements in modern conflicts. Nowadays, modern conflicts, they use generally high explosives in their weapon. After Second World War, many tests with new materials against explosives was done because the behavior of the structure when this structure is subject for blast effect coming from weapon, aerial weapon. People started to study this in the last century after Second World War. Verification of construction ability to withstand is one of the goals we can find in these papers that people work about explosions. Terrorist actions increased research in this area. Also, we can see here a picture of a terrorist action. The structures to protect people and buildings, people are studying about this. New materials like glass fiber reinforced plastic and the fiber reinforced plastic. People are also testing in field tests with explosive. Field tests increased after the Second World War, and loss of life in explosion has been a concern for everybody that are people that are studying this area of the science. Shockwave, blast effect, and fragmentation. So talking about shockwave, about 300,000 bars and 3,000 to 4,000 degrees Celsius is the temperature and the pressure that you can find in a chemical explosion. And shockwave begin to compress the air surround the explosion, and this action bring many damages for the structures and people. And when the explosive have metallic casing, there is a high energy of fragments also bring damage for people and for structures around the explosive area. Full-scale field tests to verify structural behavior people are doing, and the researchers are working with this kind of science. Talking about material and methods, the characteristics of the field test, the material, framing material, it's important we have to define the concrete compressive strength. We also have to define the thickness of the slab, the reinforcement spacing, what is going to influence the reinforcement ratio, and the explosive charge weight in TNT is other characteristic that must be defined for field tests. Standoff distance and scaled distance. Scaled distance is one parameter that is very important. And the damage that was observed, the visual analysis. These topics we developed in the material and methods for the characterization of the field test that we are going to analyze. So the comparison of the structural damage, we could use the scale distance and the reinforcement ratio that is defined by these equations that we can see here. The equations of the reinforcement ratio is the cross-sectional area of the steel over the cross-section of the concrete area. And here we did a description of damage and in four levels. We can see here the definition of the levels. Level 1, just apparent damage not observed. Level 2, cracks, fissures, and detachment of small parts of the observed without altering their original shape. And level 3, additional to the damage, we can see the rupture of the concrete section and keeping sometimes the reinforced and preserved, but the structural elements preserved curvature. Level 4, the complete destruction of the concrete structure with the rupture of the concrete area and also the steel. So here we have the equation of the reference value that we have the reinforcement ratio, the scale distance, and a number to standard to give a standard value for the comparison. So the results in analysis after the explosion, here we can see one of the explosions of the one test that we are going to analyze. We are going to analyze two tests, two different papers, two different works. Here is the first one, and this after the explosion we can see here that the slab was completely destroyed. It's level 4. Here we could put the parts again in the position, original position, and we can see here the part where the shock wave shocked against the slab and brought that damage. Here is the second paper. The second paper is this one here, that the slab is a little bit thin than the other one, and here the TNT, the position of the TNT with the standoff distance, and here we can see the results. The number of these slabs is the number that we put for the comparison. Here is slab 10, upper and bottom face is the first line here. We can see that the upper face where the shock wave shocked against, we could see some parts of the cracks are similar to the paper before we saw in the slide before. And the second line, we can see here the slab 11, the upper and the bottom face, and we could see here that the damage was higher. And we're gonna see in the table why these damages are different for the same test. Here we can see the slabs, the numbers of the slabs. We could see slab 10, slab 11, the FC key, the strength, the compressive strength of the concrete. Here is the FC key, and the reinforcement ratio. Then we can see here the column with the scaled distance, and the last one is the support, the system of support for the slab. Here we can see then slab 1 to slab 7, they were just double supported. Slab 8 to slab 11, they were double fixed. It's the second experimentation. So we have 1 to 7, the first experimentation, and 8 to 11, the second experimentation. And we're gonna see the classification of the damage that we could see. You could see that slab 10 and slab 11, the difference was actually the scaled distance. So slab 11 with a lower scaled distance, and this slab 10 a higher scaled distance. So a higher scaled distance could bring less damage than the lower scaled distance. Here the results, we could use the reference value equation. For smaller scaled distance, values slight variation can lead to significant different damage level, as evidenced by the test on slab 8 to slab 11. It was easy to see when you could see the picture of slab 10 and slab 11. It was a slight variation, and you could see a very different damage. So the classification of damage level, we could see that damage 2 to damage 3, slab 10 to slab 11. We did the same comparison for the other slabs and the other slabs for the first test 1 to 7. And working with the equation, we could find the last column of this table and could do the classification of the reference value. What's important to see the analysis is that the result of the relationship proposed in VR equation was consistent only when used in isolation for the same work, when the changes in reinforcement rating and the scale distance are subtle. With the same analysis in the work, the smaller than z value, the greater the qualitative analysis of damage. The damage thresholds can only be applied to experiments with an initial boundary condition. So, the similar boundary condition. So, the experimental conditions vary in terms of concrete compressive strength, reinforcement ratio, near cross section, standoff distance, explosive weight, intensity equivalent, and slab support conditions. This variation, when not significant difference with the same experiment, did not result in abrupt changes in the damage classification according to the proposed scale. For experimentation maintaining the same boundary conditions, with variation in material characteristics and proposed and decomposed explosive, the method presented here can provide qualitative predictions according to the development damage scale. So we can see that when you use this method for the same experimentation, this method works very well. But when you compare different boundary conditions, sometimes this comparison is not so good. So we can use this method for the same boundary conditions. Thank you very much. Here is my contact.